Yeah, so I'm Brad Chamberlain. I'm a principal engineer at Cray, and I'm the technical lead for this language I'll be telling you about today called Chapel. I wanted to start with just some kind of ground rules, I guess. First of all, I wanted to express my sort of huge respect for all of you guys. I was looking at the agenda only focusing on kind of my day, and I'm like, oh, this looks interesting. And then I looked at it last night in more detail and saw you guys are here for massive amounts of time. So I'm really impressed with the program and with you guys for doing it, and I'll try to do what I can to keep you awake here sort of at the end of the day before dinner. And with that, I'm going to tell you about Chapel. Chapel is probably pretty different than most of the other technologies you're hearing about in this school. It's probably one of the most speculative languages going on in the sense that it's not as deployed as MPI, OpenMP, UPC, even Charm++. It's also kind of one of the less mature technologies, but many users in HPC have been finding it sort of attractive and compelling and are really sort of rooting for it to succeed and get mature enough that they can use it. And I think that's part of what led to the invitation to present to you here today. So it may not be something that you can use in your work today, unless you're doing language research, and then it may be a great platform for you. But hopefully it's something that over time will become more and more mature, and you will be able to use it. And whether or not Chapel succeeds and this specific language succeeds, I think the concepts here are important concepts that seem to be showing up more and more in programming models. So perhaps pay attention to the concepts even if Chapel itself is not appealing to you. So this is a slide that the Cray marketing department put together in about 2008 or 2009. And the brag here on the part of Cray was that for looking at sustained performance on a real application, not just on a benchmark or a stunt or something like that, the claim was that those milestones, sort of the first sustained gigaflop, teraflop, petaflop, were all achieved on Crays. And you can kind of see here what the machine name was, how many processors were used, and what the application type was. And this was sort of used, you guys are looking forward to sort of exascale computing, and so are we as a community and a company. And so the claim was, well, we want to be the first company to get to an exaflop as well. We don't know what that'll be called. It's going to be a whole bunch of processors. We don't know what the application is. So when I saw this slide as a programming languages and programming models person, the thing I was curious about was, well, how were these different sustained performance milestones programmed? And so I went and did some research, and these are the answers I came up with. So that first gigaflop was written in Fortran 77 plus Cray autotasking and vectorization, which are essentially ways of getting the compiler to implement parallelism for you, primarily around loops and things like that. And then we had this mode change that occurred, and that's the world we've been living in for the past few decades, where message passing was introduced when we went to the teraflop. So that was the first time that MPI came into the picture, and that's pretty much, as you've heard this week, been the de facto standard for most parallel computing at large scale ever since. So when we get to the petaflop, you see that MPI is still there. Some C++ has come into the mix, very modern language. And vectorization has sort of come back into the fold again. But when we look to the exaflop, people are expecting another one of these mode changes, like the one that occurred when MPI came into the mix. So if you were to ask someone today, what's the conservative bet for what we're going to program that exaflop in, they would say, well, it's probably going to be some combination of C, C++, and Fortran, probably MPI for the internode concerns, and then something like CUDA or OpenCL or OpenMP or OpenACC, something of that ilk within a node. Okay, and you guys have probably heard why this is this week already. When we look at sort of next generation processor technologies that are coming out, we're seeing things that are pretty diverse and pretty different from what we've been using for the past few years and past few decades. So nobody knows quite what these are going to end up looking like, but these are 4 processor designs that I think are characteristic of sort of the directions things are going. So the Intel Mic, the AMD Trinity chip, NVIDIA's Echelon architecture, which came out of a DARPA program, and then a Tilera chip, which you may not be familiar with. It's probably most similar to the Intel Mic. It's basically a 2-dimensional tile of processors. And while these designs all differ quite significantly from one another, there's some general characteristics we can make about them, which sort of, I think, points to the direction we're going as a community. So most of these designs have either increased hierarchy within the processor or at least increased sensitivity to locality. Right? You have to be more aware of what's here and what's there within a compute node, whereas typically we haven't had to worry about that as much. And the other thing is, some of these designs start to introduce heterogeneous processor and memory types. So you start off thinking about, I want to run this on processor type A versus B, or I want to store this in memory type, X versus Y. And the point here is that, next generation programmers, which is hopefully all of us in this room, will suddenly have a lot more to think about within the node than we have in the past. So that's why we end up with this sort of smorgasbord of programming models down here. The last one is kind of the CUDA OpenCL OpenMP category is designed to talk about well, we need probably some kind of technology to talk about how to program these next generation nodes. But the interesting thing to me as a programming language designer is that when you go through these phase changes in architecture, this is also a time we can potentially do something completely different, maybe something better than just kind of continuing to mash programming models together. And so what I'd like to do is illustrate that through a really, really trivial example. This is a simple benchmark, really one of the simplest parallel programs you could write called stream Triad. And basically what you do in this benchmark is you take a vector C, multiply it by a scalar alpha, add it to a second vector B, and assign that to a third vector A. And this is designed as a memory-intensive benchmark. I don't mean to put this up as like, this is the killer app for HPC or anything like that, but it's just kind of a nice, simple cartoon to talk about programming models with. So the obvious parallelization here is to just chunk up those vectors into approximately equal size chunks, and then have each of your parallel tasks do the computation on its subvector of the total vector. And if we were to run in a distributed memory mode, then we would do more or less the same thing. The one thing I've drawn differently here is we would take that scalar alpha typically and replicate that across all of the nodes so that I don't have to communicate to get the value of alpha. I've got my own local copy right here that I can use. And of course, the world we're living in today is one in which we typically are doing a hybrid between distributed memory across our nodes and then shared memory like multi-core within our nodes. And so you end up with a picture like this, where you've got sort of the two styles of parallelism going on. Now, if we look at this in terms of code, and I'll warn you the code is not going to be particularly readable, but you'll get the gist of it. This is what stream Triad looks like in MPI, and the colors are barely coming through on this projector. There's some red code here, which is basically the MPI code. There's a green loop down here, which is basically the computation we're trying to do. And then the black code is basically just kind of boilerplate that comes out of C programming to an extent and SPMD programming to an extent. And there's not very much MPI here because this is an embarrassingly parallel program. So it's basically sort of set up and tear down. But there's not communication to speak of, and therefore not a lot of MPI. So now if we want to make this into that hybrid code I was talking about, well, we could decorate it with OpenMP. And so we end up with some blue code that was introduced up here at the top, and then around a few of our loops to assert that they're parallel. And now we have the hybrid code that's both distributed memory parallel and shared memory parallel. And the thing I want to point out here is I've given you basically the simplest parallel program I can think of, stream Triad. And the way we talk about parallelism and locality, which I would say are the two things that programmers ought to care about in parallel computing at large scale, are expressed in completely different ways here, right? The notations we use, the concepts, the features are completely different. And I think that's kind of unfortunate because this is a really simple case. And as you can imagine, as you get to more and more complicated programs, the way you'd express these things would diverge in greater and greater ways. Now if we look at how might I target a GPU today, well, if I use CUDA, this code on the right over here is the CUDA version of stream, and the purple code is all of the stuff that's specific to CUDA. You can imagine I could also mix this in with the MPI and OpenMP. But again, the point is, without going through this in great detail, the concepts you use in CUDA to talk about, again, parallelism and locality, the two things we care about, are again completely different than what we use in MPI and OpenMP. So the thesis of my talk, and to an extent of the Chapel project as a whole, is that in the HPC community, we suffer from having too many distinct notations for talking about the two primary things that we should care about. Parallelism, what should run simultaneously, and locality, where should things run and where should things be stored. So how do we get into this situation as a community? So I would say that arguably the way we got here is that the HPC community has traditionally given users pretty low-level, pretty control-centric programming models. So they tend to be built pretty close to the target hardware, and they tend to support abstractions that sort of fit what the hardware can do pretty well. And as a result of that, they also tend to only support a single style of parallelism. So what I've got in this table here is kind of different types of hardware parallelism that you might expect, like internode or vector capabilities or GPUs, and then the programming models that we typically use to program those today, and then the unit of software parallelism that those programming models support. And so what tends to happen here is that if I want to target multiple levels of hardware parallelism or express multiple kinds of software parallelism, I typically have to start mixing and matching these programming models together, and that's where you end up getting these hybrid programming models. So this is not all bad. The benefits to doing this, the reason I think we've done this, is it gives the user lots and lots of control. Sort of if the machine and the architecture can do something, you can probably do it too, because these are pretty low-level models. And they're also fairly easy to implement, right? The lower level you are, the closer you are to the hardware, probably the compiler or library writer doesn't have as much work to do. But the downsides that I've been arguing are that there tend to be lots more user-managed detail. You have to deal with the fact that you're dealing with different notations for different types of parallelism. And I think as a result of those things, the code ends up being much more brittle to changes. That can either be changes in your algorithm, like I want to change this from a 2D to a 3D decomposition, or changes to the architecture. And that's what we're seeing today as we move to these GPUs and mics and things like this. Our traditional program models are not quite holding up. So sometimes when I give this talk, probably not to you guys, people's reaction is, well, gosh, I'm glad I'm not an HPC programmer. Seems like you guys have a really raw deal coming up. Maybe some of you who are younger students are thinking, well, I can still get out of this and go do graphics or something like that. But I think the unfortunate reality here is that these compute nodes that we're looking at aren't just sort of the future of HPC compute nodes. This is also the way mainstream processor designs are likely to go as well, because of hitting sort of the clock speed wall and people continuing to want lower power and higher speed and so on and so forth. So, performance-minded programmers in the mainstream also are increasingly going to have to deal with parallelism. They already are today. And as the chips become more complex, locality is going to become more and more of a concern there as well, which is interesting because traditionally only sort of, us lofty HPC users have really had to worry about locality in any big way. Okay, so going back a couple slides, I said, I think HPC suffers from too many distinct notations for talking about parallelism and locality. Of course, being a language designer, rather than saying, so let's stop there, I'm going to introduce one more language. So this is what the stream triad computation looks like in Chapel. And as you can see, you can probably almost read it, unlike the other ones. As you can see, it's pretty concise, and a lot of this has to do with the fact that we've sort of borrowed a lot from modern programming language design and scripting languages and things like that. So we've tried to get sort of a similar kind of fast and loose feel to what you might have in like a Python or MATLAB or something like that. And by the end of this talk, you'll probably understand most of this code, but I don't want to walk you through right now. But what I do want to say is that what's interesting about this code is that with this one program, I can run this in a serial mode, in a shared memory multi-core mode, a distributed memory mode, the hybrid mode we talked about, or really any one of a number of other ways of mapping this down to the hardware, including dynamic load balancing or different distributions, things like that. All through this one clause here, which I've elided a few details on. There's kind of a constructor call I left out. And this basically is this thing called a domain map, which says, here's how I'd like you to map this index set and any iterations over it and any arrays over it down to the architecture. And by changing that clause, we basically can end up with any one of these different implementations of how this computation, this sort of scale and add these vectors, gets mapped down to our parallel hardware. So the philosophy here in Chapel is that with a good language design, you can tease the details of how you're going to map locality and parallelism down to the hardware away from the actual algorithm that you, the scientist, care about. And that this permits the compiler and the runtime and the application scientist and the parallel expert to all focus on the things that they do the best, without kind of entangling all those things together in the code. So what we're going to do over the course of this talk is by the end of it, again, you'll sort of know most of these features. We'll sort of build our way up to these domain maps, which are kind of the highest level concept in the language. But for now, this is just kind of a teaser to whet your appetite. All right, so the outline of this talk is as follows. I've just given you a little bit of motivation, like why are we doing Chapel and what's kind of different and unique about it. And next what I'm going to do is go into some of the background about Chapel, where did it come from, and some of the motivating themes. Then we'll go through a tour of the language. It won't be a complete overview of everything in the language, but it'll give you a flavor of different feature sets that are in the language. I mentioned implementation there, but in fact, I ripped out all the implementation slides from this talk. I just forgot to update my outline. And then towards the end, I'll wrap up with a little bit of status on the project, what our next steps are, and time permitting, some of the research problems that we're working on currently. All right, so what is Chapel? As you've probably gathered, it's an emerging parallel programming language. The design and development of Chapel are being and have been led by Cray, but we've always done it in a very collaborative manner. So there are a number of people in the Chapel community who are in academia, at national labs or international labs, a few in industry. The language itself came out of the DARPA HPCS program, which ran over about the past decade or so. HPCS stood for High Productivity Computing Systems. And so basically the goal of the program was to say, we as a community are really good at building faster and faster and faster machines, but we're not particularly good at making them easier and easier and easier to use for a broad community. So the goal of the program was really, how can we make the machines not just faster, but also more productive? Cray investigated a number of technologies under this program, one of which was this Chapel language. There are several other things as well that I won't be talking about today. So the goal of Chapel is to improve the productivity of the programmer. Right? You have to write some code to run on this machine. We want to make your life easier. And so the first thing we want to focus on is making the machine much more programmable than it is today. At the same time, since performance is king in HPC, we don't want to sacrifice performance. So, Kathy argued in her last talk that you can use PGAS languages and not sacrifice performance. That's something we're betting on as well. We want to support better portability than current models. And your first reaction there might be, well, MPI is quite portable. How could you be more portable than that? But I think the fact that sort of MPI becomes insufficient in and of itself in a machine that has GPUs is an example of how we want to be portable to sort of changes in the architecture, things like that as well. So you don't have to start building hybrids out of Chapel. And the last one where we have the least impact is improving the robustness of parallel codes. And here we just talk about sort of removing common error cases and making other errors easier to figure out. But in the HPCS program, most of our robustness work took place more in the hardware and operating system level. And then the last thing at a high level I want you to know about Chapel is that it's a work in progress. So the language and the implementation are still very much actively being developed. That's bad if you want to use it today. You can use it, but it's not incredibly stable and robust and fast yet. But the good thing is, if you kick the tires and you give us feedback, it's not too late to improve the language if you think we've done something wrong. So speaking of the implementation, Chapel is being developed as open source software at SourceForge. It's licensed as BSD software, so it's quite permissive. You can pretty much do what you want with it. And people often assume that because Cray is developing Chapel, it only runs on Cray machines. But we've designed both the language and the implementation to be incredibly portable. So we, of course, run on Cray architectures, but we also run on multi-core desktops and laptops. I do a lot of my development on this Mac, especially when I'm traveling. You can run on commodity clusters, systems from our esteemed competitors. And something we haven't done much with yet, because it wasn't part of the HPCS program, is we haven't done much yet to target accelerators, so GPUs, mic, things like that. That's current work, and again, that's something I'll touch on a little bit at the end, time permitting. But again, the goal here was to design a language that was not locked to any particular architecture. It should be able to target any parallel architecture is the idea. And I wanted to give you just a very high-level schematic of what Chapel compiler looks like. From a user perspective, it looks like any other compiler. You feed it some source code and maybe refer to some standard modules, which you can think of as like libraries, and you get an executable out. So diving under the covers a little bit there, you can see a little more in details. The heart of the compiler is this Chapel to C compiler here. And I call it a compiler rather than I think Kathy called hers a translator, because it is really an optimizing compiler. It's just that it generates C rather than assembly. We link in some internal modules, which we actually try to implement a lot of the language in Chapel itself to take advantage of its productivity benefits. And then we generate some C code, run that through your standard C compiler and linker, and then we link in runtime support libraries that implement things like the parallel tasks and the communication between nodes and the memory management and things like that. And all of these libraries are implemented so that you can plug in different implementations. If you have a different tasking library or threading library you want to plug in, you can do that, or a different communication library. And so out of that, you get the Chapel executable. And the reason we take this approach is primarily for portability. Right? By doing this, we can basically focus on the things we care about, the parallelism and the locality, let the C compiler worry about things like the low-level instruction scheduling, register allocation, things like that. All right, so the next thing I want to talk about is what I call these 5 motivating themes for Chapel. And you can think of these as being, if you're asked to design a language and you're going to start from a blank sheet of paper, you need to decide what are we going to put in the language and what are we not going to put in. And more importantly, what are we going to use as a deciding factor whether to put something in the language or not. And so these 5 themes are really, you can think of the 5 things that we used when we were trying to figure out what was this language going to look like. And this is just sort of a laundry list, so I'm going to break it out over the next several slides. The first thing is we wanted Chapel to support general parallel programming. We've already touched on this a little bit. You can think of this as, if you have a parallel algorithm in your mind, and you have some parallel hardware you want to run it on, you should be able to write that in Chapel. You should never hit a point where you say, well, Chapel was nice while I was doing, say, data parallelism, but now that I want to do something else, I need to go back to MPI. And another way you can think of this theme is that if you think of that table that I showed you before, showing different types of hardware and software parallelism, what we'd really like to do is sort of replace this middle column with Chapel. That's not to say we want all these other program models to go away. We just want Chapel to be a model that works in all of these scenarios and exists as an alternative to the other models that we have today. Okay, so that's the first theme. The second theme is these things that we call global view abstractions. So let me define this. And I like to define it with a very simple example, slightly more complicated than the stream Triad benchmark. So I ask you to apply a 3-point stencil to a vector, say replace every interior element with the average of its nearest neighbors. This is probably the picture that comes to your mind. I want to take sort of the dark purple elements from the first view of the vector and the dark purple from the second view, add those together, divide by 2, and assign to the dark orange in this yellow vector. So in practice today, if you're doing this on any kind of scalable machine, in almost every language that you might use, the way you would write it is using a local view. You're going to write code that talks not about the algorithm overall. You're going to talk about what should each unit of parallelism do, what should each task or process do. And so one of the first things you're going to do is say, OK, well, let's divide. If I'm running on 3 tasks or processes, say, let's divide up our data structures across those tasks. So each one's going to get 2 elements of each of my vectors. And then for a stencil code like this, it's typical to allocate some extra space in order to cache values that you don't own, but that you need to compute the values that you own, and then to do some communication to update those cached values. And then at that point, you can do the computation you originally set out to do, that averaging computation. But of course, again, you're writing it from the perspective of one of these parallel tasks, not the whole global problem size. So the whole idea behind the global view is you'd like to be talking and thinking and writing code about sort of the data structures as a whole rather than one process's view of the data structures. So in code, the way this looks, and this is Chapel code, The global view looks like this. We basically declare a global problem size like n. We declare some arrays over that global problem size, and then we do our loop in terms of that global problem size as well. And this looks a lot like what you'd expect in sort of a sequential language, because they're sort of global view in a degenerate way. And we also talk about this having a global view of control flow in the following way. So when I run this code, when I run a Chapel code, the conceptual model is that a single task is going to start running your main procedure. And then there are features within the language that add and remove parallelism. Like this for all loop, for example, says, execute this loop in parallel. So that'll create parallelism, which will conceptually be destroyed after the loop's over. So this is something you saw in OpenMP as well. It's sort of also a global view model of parallelism. But again, things like MPI and most of the traditional PGAS languages use more of a local view or SPMD model. So in that model, things look like this. You write your main procedure assuming that not one copy of it is running, but many, many copies of it are running, and that's where your parallelism is really coming from. Right? So all the blue code on this right side of the slide is things I had to change from my conceptual global view code in order to get this local view code. And I've sort of written this as kind of a pseudo message passing code, basically. Okay, so I'm going to take my global problem size, query how many processes there are, and what my unique ID is. And I'm going to compute what portion of the global problem space I own by dividing the problem size by p. So I then declare my arrays in terms of that local problem size. And again, I'm going to extend by 1 in either direction so I can get these nice ghost or overlap cells to cache neighboring values. And then I insert some communication, again, using kind of a pseudo send-receive thing here, to basically update those caches. And then I can do the computation itself, again, in terms of my local problem size. So this isn't that bad. Any one of us could probably write this. You guys spent a whole day on MPI, as I understand it. Except for me, I wrote this code and gave this talk for a month or two before one of my colleagues said, you know, you've got a bug here. Your last processors basically are indexing one too far outside of the bounds and kind of falling off the edge. So you know, anybody can write this except for me. So you can fix this, of course. So I have some purple code here, which basically keeps track of what those extreme bounds should be. And I'm going to use those to drive my loop down here. And I basically nudge them in for those extreme processors. Okay? So now I've got a more or less correct code. Except that I've written it assuming that the problem size divides evenly by the number of processors. Of course, I could write more code to sort of give some processes the floor of n over p and others the ceiling of n over p, or use some other kind of way to deal with the extra elements. But then I ran out of space on my slide and patience. And if you've looked at MPI code in practice, sometimes people do this, right? It's kind of a hassle to deal with these kind of things. So let's just put an assertion that it divides evenly. And that's great until you want to run on, you know, a non-power of 2 processors or something like that. The other thing to note here is that I said, you know, this isn't that bad, and it's not. But this is, again, sort of about the second easiest parallel program you could write. And as you get from this one-dimensional stencil to two-dimensional and three-dimensional stencils, all of these details sort of explode geometrically. Because suddenly you don't just have 2 nearest neighbors, you have maybe 26 nearest neighbors. Then it doesn't fit on a slide so well. All right, so this is the global view. We want you to be writing and thinking, or at least able to write and think the way the code looks on the left over there. And able to is really a key distinction here. Because a lot of people say, well, I'm an HPC programmer. I need to control everything because I'm a control freak, and I need every last scrap of performance, right? And that's a completely valid perspective. So one of the big themes in Chapel is to provide easier ways to do things, provide these global views, but not take away your ability to do things more manually. So for example, if you wanted to write an SPMD program in Chapel, you can do that. And this is a little idiom that would show you how to do it. And again, you'll understand all this code by the end of the talk. Okay? So global view doesn't necessarily mean you can't do local view or SPMD programming. It simply means you have an alternative to doing it. And that's the second theme. All right, the third theme is this concept we call multi-resolution design. And here's the motivation for this. So most of the things we use in practice, I've argued, are kind of lowish level, kind of close to the target machine. And again, they give you a lot of control and a lot of performance. But there's a point at which I start saying, you know, why am I writing this stencil idiom again? Maybe it's just that I'm a terrible software engineer. Could be. But at some point, things just start to feel really tedious. And I feel like I'm spending more time wrestling with the programming model, the algorithm, or sorry, the programming model than the actual parallel algorithm that I want to be writing. And not all programming models have been low level like this. So there have been higher level programming models proposed over time. Most of them have not caught on. 2 that are kind of near and dear to my heart are High Performance Fortran and ZPL, which were 2 high-level programming models that came out in the 90s. And these both have these nice data parallel abstractions, global view arrays like the ones I said Chapel had. But they sort of stranded you away from the machine. If the abstractions failed you, there was no recourse, no manual override you could use to get down close to the machine and control things more explicitly yourself. Or I should say that it's not that there weren't any ways to get down lower, but they felt very restricted and very much like you were escaping the language. So the result I have here is at some point I say, well, why don't I have more control? Like once my program doesn't fit that idiom, why can't I just drop down lower? And so this motivates this multi-resolution design concept we talk about. So in Chapel, our goal was to design a language that had multiple tiers of features, some of which were going to be much lower level, much more explicit, much more closer to the hardware, others of which were going to be much higher level, much more abstract. And so the way in which I said I already alluded to this is that sort of the domain maps and data parallelism are sort of the global view abstractions we talked about, and that's a way to sort of write at a very high level. But the way that you can write at the local view that I showed is basically dropping down to some of those lower level tiers in the language. So another part of our design here is to build the higher level features in terms of the lower level features in order to guarantee that they're all compatible with one another and they can move between higher and lower levels sort of from function to function or statement to statement in your program. This is also done so that the user can write their own high-level abstractions if we haven't anticipated some high-level array or parallel loop schedule that you might want in your program. And we'll see examples of that later on in the talk. So that's the third theme, this multi-resolution design. And then the fourth theme is a pretty simple one. It's that if we're running on these large-scale machines, you need to worry about locality. You need to worry about where your data is located and where your tasks are running relative to that data in order to get good scalability. Or I should say, somebody has to worry about it. In spite of pursuing aggressive language designs, we're actually not sort of fans of heroic compilers. So we think this is the kind of thing the user should have to think about and help reason with. So the idea here is we want to give the user features that give them control over reasoning about locality and affinity. And as Kathy alluded to in the previous talk, we fit within this family of partitioned global address space languages. Or I actually prefer the name partitioned global namespace languages. Because often in these languages, you're not actually explicitly dealing with addresses so much as the names of variables. They didn't ask me when they made the name what I thought it should be called. So the abstract concept here, you see this in Kathy's talk, right? We're going to have sort of a conceptually shared namespace, but it's going to be running on distributed memory. But rather than being a completely flat shared memory where we can't really tell where anything lives, it's partitioned, so we can reason about where things live if they're in that shared namespace. And so this is kind of my version of the diagram that showed up in Kathy's talks. And Kathy actually alluded to the broad family of PGAS languages. The sort of three that usually come to mind for people are sort of the founding members of this term PGAS: Cray, Fortran, UPC, and Titanium. Where Kathy talked a lot about UPC and Titanium. Cray Fortran, if you're not familiar with it, has actually gotten rolled into the official Fortran standard now. So I think as of Fortran 2008, co-arrays are now a full-fledged feature in the language. So a lot of people, when they hear about these three languages, they sort of think, oh, these are just the Fortran C and Java dialects of the same language. And that's a reasonable assumption to make, but it's incorrect. So this is my version of a slide. Kathy had something similar to this that I hadn't seen before, but I liked because she had pictures. So a lot of people, when they say, oh, you're a PGAS language, I must know everything about you. This is sort of a slide that points out that PGAS is really just one element of a language's design or a programming model's design. So we can say that Cray, Fortran, UPC, and Titanium are all PGAS. MPI, I would say, is sort of a distributed memory model. Actually, not just I would say that. Probably all of you would say it too. OpenMP, of course, is designed to be a shared memory model. And Chapel, as Kathy mentioned, is also a PGAS model. But then if we look at other things, we see other differences. So if we think about the programming model or the execution model, which for me is sort of, as a programmer, how do you think about writing code and how do you think it's going to execute on the machine? In these traditional PGAS languages, as you heard from Kathy's talk, these are all sort of SPMD models. Like the typical use of MPI, you're going to start up a bunch of copies of main at the beginning of time, run them to the end of the time, and that's your parallelism. Unless you start bringing in hybrid things like threading libraries and stuff. And to me, then you're sort of mixing programming models, which is fine, but now you're not just in UPC anymore. So MPI uses cooperating executables as its programming and execution model. Again, in most cases, it tends to be SPMD in practice. OpenMP has what I call global view parallelism. Again, this creation and destruction of parallelism within the code. And the execution model is a shared memory multi-threaded scheme. So Chapel's very similar to OpenMP in this axis. It also has global view parallelism. You create and destroy parallelism as your program runs. But our execution model is distributed memory multi-threaded. So rather than being constrained to a shared memory, we're going across multiple memories. As you'll hear later on tonight, OpenMP is looking at having distributed memory within a node as well, so arguably they're sort of going in this direction. But historically, it's been sort of restricted to shared memory. And then if we think about other things that you might care about as a programmer, like what kind of data structures does this language have, or how is communication expressed in this model? This is interesting because this is where the traditional PGAS languages are quite different in this regard. The data structures they provide are very different from one another, as befits the base languages. So Cray Fortran has sort of multi-dimensional global arrays, and as you heard, UPC has kind of one-dimensional and pointer-based arrays because it's an extension of C. Also, the communication is very different. In UPC, a lot of the communication is implicit. You just happen to refer to an array element that lives somewhere else. That's communication. In Cray Fortran, it's all very explicit in the syntax. So again, MPI here is the data structures are manually fragmented. You're sort of, again, allocating what does one process or what does one task own. Communication is done through APIs. In OpenMP, of course, you're shared memory, so you're just using whatever shared memory data structures you want. Communication doesn't really apply. In Chapel, again, we have these global view arrays, and the communication tends to be implicit as in UPC. So when I evaluate the traditional PGAS languages, Cray, Fortran, UPC, and the like, these are what I think their strengths are. They support this shared namespace, which is a lot like programming shared memory. And the conventional wisdom is that shared memory is sort of nicer, easier, more friendly to program, which maybe is not always true, but if you believe that, then you get that benefit here. It also supports a strong sense of ownership and locality. So again, you can reason about sort of where things live and where things are running and where they are relative to one another, which again is very important from a scalability perspective. And the last one is sort of having the compiler deal with the communication by just naming things that happen to be remote. Makes the user's task much more easy. It also means the compiler can sort of use whatever mechanisms are best on a particular machine to communicate. But there's some downsides to these traditional languages. The first, I think, is that being restricted to this SPMD programming model is, I think, too restrictive, particularly as we look at exascale machines where things are more hierarchical. You might want to fork something off to run on an accelerator or something like that. Again, you can get that if you start mixing in pthreads or OpenMP or something else with these. But again, being a purist, I'd rather use a single model that sort of did it all for me rather than starting to mix and match different things and trying to figure out how they played together. The second one is the data structures, I think, are not always as flexible or as rich as you might like. It's like the fact that UPC arrays are restricted to the 1D case. And the last one is that I mentioned that shared memory isn't all sort of roses and happiness. So if you've used shared memory, there are problems with kind of race conditions, memory consistency models, things like that. And these PGAS languages have those problems as well. I should say that Chapel does a lot of work to address the first two negatives here, but we still share the third one. And in fact, it seems very tough to me to be a PGAS language and not sort of have these hazards of shared memory programming. So maybe someone smarter than me can prove me wrong there, but I think that's a tough nut to crack. So that's the fourth theme about locality and affinity. And then the fifth and last theme is to try to reduce the gap that I would say exists between the languages and programming models we use within the HPC community and those that are used in mainstream computing. So what I mean by this is if I talk to a student who's just graduated, say, with a bachelor's in computer science, and I say, well, what kind of languages do you use? I usually get answers like, well, Java, Python, MATLAB, maybe some C#, maybe some C++. And then if we hire them into the HPC arena, we say, well, here's Fortran. And if you're lucky, here's some C++ and maybe some C. And here's this thing we use called MPI, which is unlike anything you've seen before. And I think that a lot of students have this reaction like, oh, wow, did I just step into a time machine and go back 20 or 30 years? So what we'd really like to do is kind of narrow the gap between these communities, both to kind of benefit from modern language design. Java and Python, things like that aren't just newer. Like they did some things really smart that I think we could benefit from as a community. And also to obviously better utilize the skills of these entry-level people who are coming out rather than having them all go to the Googles and Microsofts and never come into HPC. While we're doing this, we're trying to walk this balancing act of not ostracizing a traditional HPC programmer. So I've definitely talked to sort of HPC programmers at national labs who say, I just don't think in terms of objects. It's not natural for me. If you were to force me to do that, it would be a big hit to my productivity. So an example of how we deal with that kind of tension is Chapel's a language that supports object-oriented programming. You can use it if that's the way you think, but it's not a very pure object-oriented language. So it's not like a Java where everything is an object. It's sort of an optional piece of language you can leave aside and you can program in much more sort of traditional block imperative style if you prefer. And that's this fifth theme. So I've been doing a lot of talking. This would be a good time to pause and see if there are any questions before I go on. But at some point, I'm going to sort of get to the lowest level Chapel features. And then if I wanted to go further, what are my options then? And so we have a couple of answers to that. So one of them is that we think it's important for any new language to support interoperability. If you look at sort of the success of Java or Python, I would say a big reason that they weren't just sort of poo-pooed as, well, that's nice, but I've got a lot of C code, is that they had a really strong interoperability story. So one of the ways in which you can go even lower than Chapel is you can basically call out to external C routines, write code there. And we even have a new capability where you can actually write C code sort of in line with your Chapel program. It's sort of in the same flavor as writing inline assembly in a C code. So that's one way you can sort of get out of Chapel and down further. And then what's down there awaiting you depends a lot on, I showed the runtime architecture and I talked about how you can plug different implementations in. So it kind of depends on what choices you've made there. So if you were running over, say, the GasNet runtime, then you would have access to kind of GasNet and anything it was running on top of. We've talked about doing an MPI+3 runtime using the new single-sided things. If you're running over that, you could code down into MPI. Another way that I think you could get lower level without kind of completely escaping the language is to provide libraries which basically wrap external capabilities. So for example, we haven't done this yet, but we've talked about writing a Chapel BLAS library, for example, that just wraps and calls out to the traditional BLAS routines. And we've done that for some other libraries, like the GMP library that gives you multi-precision math. That's something we've wrapped, so you can call out to that library. And one of the things we've talked about and wanted to pursue with Argonne, but nobody's quite found the time or funding yet, is actually, I said that you can do SPM deprogramming in Chapel. Well, you could support an MPI interface in Chapel as well, and basically use that. Or at least I believe you could. So I think those are some ways in which you can sort of get even lower level in sort of the concepts that Chapel provides. So we're going to start with the base language. And you can think of the base language as being sort of, if you took Chapel and you took out everything related to parallelism and related to large-scale computing, that's what you'd be left with. So in a sense, it's like the sequential C or Java or Fortran on which Chapel is based. But rather than extending an existing language, we really started from blank slate, although we certainly were greatly influenced by many existing languages. And so you'll see things that look familiar to you. So let me show you a few features in the base language. One of the first ones is that Chapel supports static type inference. And what this means is that in most any context, you can leave off the type specification in a declaration, and the compiler will fill that in for you. Now, this is completely optional. If you prefer types from a documentation standpoint, or to sort of keep yourself sane, or make sure you don't lie to the compiler or whatever, you can specify types in all these cases. I've just left them off for the purposes of this slide. So just to run through some examples, I start out here, and I declare this constant called pi, and I initialize it to 3.14. The compiler knows that 3.14 is a real floating point literal, so it determines that pi is a real floating point constant. Then this next one, chord, I assign 1.2 plus 3.4i. The compiler knows that if I add a real floating point literal and an imaginary floating point literal, I get a complex. So it knows that chord is a complex. And it knows if I multiply a complex by a real, I still get a complex. So chord 2 is a complex. And similarly, name is a string, and verbose is a Boolean. Okay, so in the declaration context like this, if you leave off the type, you have to have an initializer, and the compiler is going to determine the type of the symbol based on the initializer's type. Okay, you can also leave off types in a procedure context. So here I'm defining a procedure called Atom. It takes 2 arguments, x and y, but I don't declare the types of those arguments or the return type. And what this gives me is a very generic procedure, and what will happen is the compiler will inspect the call sites and basically stamp out versions of this procedure for any of the signatures that it needs, much like a C++ template, but without all the angle brackets. So for example, if I say call Atom on 1 in pi, the compiler determines that, okay, well, x is going to be an int and y is going to be a real. When I add an int and a real, I get a real. So the result of Atom is going to be a real, and sum will be a real. And we happen to overload plus to mean string concatenation, for better or for worse. So if I add name and forward together, the compiler knows that that's a string plus a string. That gives me a new string. So full name will be a string, the one my mom calls me when she's mad. So this just sort of shows that in a lot of contexts where you normally are used to declaring types, you can leave them off in Chapel. And the goal here is really to support the ability to quickly sort of sketch out code and then go back and refine it later, much as you would do in a scripting language like Python or MATLAB or something like that. All our numerical types are 64-bit precision by default. So if I just say 3.14 there, pi is going to be a 64-bit real floating point value. If you wanted, say, a lower value, or if you had a machine that had a higher value, you could do that either by explicitly declaring the type or by casting the literal to the type that you wanted. So if I said 3.14, cast that down to real 32, pi would have been inferred to be a 32-bit real. Can it always be determined at compile time what the types are? And we've designed the language so that, yes, that's the case. In particular, we wanted to not incur any of the overhead that a dynamically typed language would have, which we thought was important for the HPC community. So yeah, every symbol will have sort of a single type over its lifetime, and that type will be determined by the compiler. If for some reason the compiler could not determine a type, it would basically say this is ambiguous to me. But in practice, that happens only very, very rarely. So the next feature I want to show you is this concept we call a range. A range essentially represents a regular sequence of integers. So at the top here, I declare a range called R, and I declare it to be 1.10, which stores the integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are a number of operators that are built on ranges that define this sort of very simple algebra on it. First operator here is a hash operator, which is like a count operator. This says, give me the first 3 values of the range. And so if I print out those values, I'll get 1, 2, 3. There's also a by operator that's used to stride through a range. So if I say r by 2, that's going to count by 2s, 1, 3, 5, 7, 9. If the stride is negative, we start at the high value of the range and count down. So that will give me 10, 8, 6, 4, 2. And then when you start composing these operators, you get pretty interesting patterns pretty quickly. Take r, stride by 2, and then give me the first 3 elements, I get 1, 3, 5. But if I say take r, give me the first 3 elements and then stride by 2, I get 1 and 3. at first glance, these ranges and the operators may seem a little bit sugary. You could obviously do this using objects and methods and things like that. But our belief is that, particularly once you get to higher dimensional arrays and programming on sort of discretizations and spaces and things like that, that having these built into the language goes a long way toward improving the readability of the code, as well as the compiler's ability to reason about what you're doing. Last example I have here I throw on because it's an idiom we use a lot in practice. It's really just a kind of cuteness, and maybe I'm a little embarrassed about it, which is why I'm making that face. So this says 0 .. #n. And we use this kind of as C programmers who want to use zero-based indexing. So ranges always have to specify a low or high bound, or if they leave one off, they're sort of infinite in that direction. And so you find yourself typing, if you're a C programmer, sort of 0 .. n-1 a lot, which gets old really quickly. So this is our cute way to avoid it. This basically says start at 0, count to infinity, but then only give me the first n elements. So then I get 0 / n-1. Again, I bring this up not because I'm proud of the idiom, but because I tend to use it a lot in my slides. I want to make sure you're aware of it. So those are ranges. The next feature is iterators. These are a feature we took from the Clue language, which is kind of an academic language that probably none of you have ever used. It's showing up more and more, I think, in modern languages now. I think Ruby has these. I think C# may have them now. The idea is that an iterator is like a procedure, but rather than returning a single time with a single value at some point, you can put in these yield statements. And a yield statement sort of kicks a value back to the call site, but then the iterator logically continues executing. And so you'll typically use these to drive a loop. So here, for example, I've written a Fibonacci iterator. It takes in an argument n, which says, how many Fibonacci numbers do you want me to generate for you? And then within here, it's going to basically loop n times and yield a value each time, which will be sort of the ith Fibonacci number for iteration I. And so again, I typically use these to drive loops. So if I say, for f in Fibonacci 7, do write line f, I'll basically get the first 7 Fibonacci numbers printed out. Unless you guys are working in some arcane aspect of HPC I'm not aware of, you probably don't care about Fibonacci numbers at all. So you can do more interesting things like, I think this is really powerful, a tiled row major order iterator. It takes in a 2-dimensional index space and in a tile size, and what it'll do is it'll iterate through that 2-dimensional space in row major order, sort of respecting those tiles. And this is the kind of thing that's pretty clean and concise to do in Chapel. I'm using a lot of the range algebra I mentioned and some other algebra that we haven't gotten to yet. But then when I call it, it's even more compact. And the benefit here is a lot like the benefit to using normal procedures in straight line code, right? I can basically reuse this somewhat complicated idiom many times in my code just by naming it. And I can customize it through arguments, for example. Or I can change the definition in one place and change all of my loops. Right? So this is much better than sort of going to every loop that's a tiled row major order and changing it when you want to change the tile size or something like that. So if you haven't used these, when we first talked about putting these in languages, I was like, yeah, I don't know. It seems kind of sugary. Is it really on our critical path? And it's a feature that, like, if you ask me to design any language from now on, I would put this in. I think it's a key feature from a software engineering perspective. And then the last base language feature I want to show you in any detail, something that will come up later on the talk as well, is this concept of zippered iteration. So if you want to iterate over multiple things simultaneously, use this zip keyword. And here, for example, I'm iterating over a range and my Fibonacci iterator I wrote. And basically what this will do is just you can think of as simultaneously driving both of them, making sure that sort of the corresponding yielded values match up. So what I get out of here is the enumeration of the Fibonacci numbers 0 through 6, and then the Fibonacci numbers themselves. Again, a very handy and important feature. The base language is quite large. There are many, many features we're not going to hear about today. Just to run through some of them quickly, we have tuples in the language. We use those for multidimensional array indexing a lot. It makes code much more clean and rank independent. Language has been designed to be very rank independent, so maybe the best example of this, we had an intern who basically wrote a 2D AMR code, and then he could run it in 3D or 4D just by changing one compile time parameter, basically. Got features for interoperability, which I mentioned, so we can call out to C and ultimately other languages as well. We have a bunch of compile time features for metaprogramming. You can write procedures that are executed at compile time to evaluate a compile time value or a type. We have object-oriented features, and then a bunch of things related to arguments and overloading and namespace management, things like that. And that's the base language. So the next thing we're going to look at is some of the parallelism, and we'll start with the low-level parallel features, the task parallel features. So all parallelism within Chapel is ultimately implemented with tasks. And you can think of tasks a lot like they are in OpenMP. It's basically a unit of work that represents something that can and arguably should be executed concurrently with other tasks. There's some subtle semantic differences that make our tasks, I think, slightly more powerful than OpenMP tasks, but for the sake of this talk, I think they're more or less the same. So the easiest way to create a new task is this begin keyword. So you can basically prefix any statement, including it could be a function call or a compound statement with begin, and that says create a new task to execute this statement. And the original task is going to proceed on. So here I'm saying create a task to execute the write line of hello world, while my original task goes and write lines goodbye. And because these are concurrent tasks, Language says nothing about how they'll be scheduled relative to one another, and in fact, the runtime probably doesn't know either. So you could get the output in either ordering, either hello world and then goodbye, or else goodbye first, then hello world. Right? I haven't done anything to constrain that. That's the simplest way to implement a task. These are very unstructured tasks. We call them kind of fire and forget tasks. You're sort of forking something off to do something, and you're going to go on and do what you were doing. Then we have a couple of ways of creating more structured tasks. This is called a co-begin statement. It's basically a compound statement where what we're going to do is create a task for each of the statements within the compound statement. So this compound statement has 3 statements. 2 of them create a producer, 1 creates a consumer. So I'm basically going to get 3 tasks out of this. 2 producer tasks, 1 consumer task. And then the other thing that's different about a co-begin from a begin is that there is an implicit join at the end of the compound statement, which is going to wait for the tasks that the co-begin created before going on. So not until the producers and the consumer have completed will the original task proceed. And then the third one is a variation on that. This is a loop-based form for creating tasks called a Coforall, or you can think of it as a concurrent for all. And what this is it's a loop like the for loop we saw, but rather than being completely sequential, it's going to create a separate task for each of the loop iterations. So in this case, this is sort of a multitasking hello world. So each one sort of prints out, I'm task T out of num tasks. And again, they're going to be running with multiple tasks, potentially on multiple simultaneous threads. So again, the output could be interleaved in any order between these different iterations. But like the co-begin, there's an implicit join at the end of the loop. So this write line that says all tasks done will be guaranteed not to execute until all of my little hello world tasks have completed. And those are really the 3 ways to create tasks in Chapel. Completely unstructured, the sort of compound statement-based, and the loop-based forms. In these examples I've shown interleaving of output at a very coarse grain, but I haven't gotten in the case where like the first task prints hell, and then the second one starts printing hell, and you get a bunch of hells before you ever get an O from, yeah. That is not a feature of the tasks. The tasks can arbitrarily sort of interleave their execution, but our default I/O routines are written so that any given write or write line statement will execute atomically and not be interspersed with other ones. That felt important from a sanity perspective. You can use lower level write line things that don't have that property, but by default you typically want to use these. All right, so having created all this parallelism, of course, in any interesting program, or most interesting programs, you will want to coordinate between the tasks in some way. And so most coordination between tasks in Chapel is done in a data-driven manner, which is to say it's through variables and data objects that we coordinate and interact between tasks. And so there are 3 main classes of variables that we use to do this coordination. The first are atomic variables. These are something which I feel like even as recently as 10 years ago, like not many people knew about these or used them, but they're coming around more and more. C++ has recently adopted them. I think C has an atomic in its standard as well. These are basically just variables that support certain operations on them that are guaranteed to be atomic with respect to any other tasks that are running. And we really followed C++'s lead here. So if you're familiar with that, it's very similar in Chapel. So you can do things like a compare and swap, atomically add things or multiply things to a value. The second and third categories are maybe a little bit more unusual or maybe less known to you. And the next one is called single assignment variables. And these are variables where if you try to read that variable, you will block until something has assigned that variable. And in the variable's lifetime, only one thing may ever assign it. Okay, so this is a way to sort of have a task block until some other task, for example, creates some result value that it's dependent on. And as you'd expect from the name, you assign them once, and that's sort of how they work. And then the last case you can think of as a generalization of single assignment variables. These are called synchronization variables. And what they do is they store a full empty state along with their value. And what's going to happen is that the reads and writes are going to block by default until the state is full or empty respectively. So if I go to read a synchronization variable and it's empty, I'm going to block until something writes to it and fills it. And at that point, I can read it, and I will consume that and leave it empty again. Similarly, a write to a value is going to block if that value is full, waiting for it to become empty. And then at that point, it can write its value, and it'll fill it. So I have an example that shows synchronization variables used in practice, kind of a very simple one. At the top here, I use a co-begin to create 2 tasks. One is a producer, one is a consumer. And what I'm going to do here is just kind of a very simple circular bounded buffer problem. So the bounded buffer itself I'm going to represent in Chapel using this array variable called buff $, and it's an array from 0 to buffer size. And the element types here I say are synchronized reals. And what that means is that each element of this array stores a real floating point value, but it's synchronized, so it has this full empty state associated with it as well. So again, every element of the array has its own full empty bit conceptually. And so then what happens is my producer and consumer are written very simply. They basically just spin in a loop, kind of incrementing their count around and around this buffer, and either read to or write to the buffer. And so when you think about bounded buffer problems, normally you're sort of concerned about overflow and underflow conditions. I don't want to get too far ahead of the consumer or have the consumer get ahead of the producer. And the nice thing about these full empty semantics is that they basically give you that for free. If at any point the producer wraps around on itself and tries to write to something it's already written to that hasn't been consumed yet, it's going to block because that element will be full. And similarly, the consumer, if it gets ahead of the producer, is going to block because it'll get to an empty cell. So this ends up being a very elegant way to write these producer-consumer kinds of paradigms, which are pretty prevalent in tasking models. Does using these result in a lot of chatter back and forth between the tasks to figure out where we are? It doesn't result in chatter between the tasks themselves because it is all a data-oriented thing. So what you should really think of it as is it introduces overhead to accessing that variable. If the two tasks are distributed in two different places, the data has to be in one of those places. So you're right. If I'm the producer and the data is local to me and you're the consumer, you're going to have to go across the network to get that. But what you can imagine is a good implementation of the runtime, if you go over and try to read it, you should sort of block there until it becomes full, rather than, for example, pulling across the network over and over again. Our implementation does that. I think most of the sort of task parallel, highly synchronous stuff we've done, at least from a performance perspective, has been local to a locale typically. We do use them across locales, but typically not for this kind of fine-grained producer-consumer stuff. It's more for kind of tree combinings and things like that. So these synchronized variables do introduce some overhead, both in terms of space and time. Accessing a synchronized array element obviously takes more time than it would for a normal one. But it's sort of a productivity feature, right? It's much more elegant than if you were to deal with pthread mutexes and condition variables and things like that yourself, which in many of the implementations is what's really going on underneath. And then you've actually seen the vast majority of the task parallel features in the language. There aren't too many more. The two that we currently have that I haven't mentioned, I'm not going to go into much detail today, is that we have serial statements that you can use to dynamically squash parallelism. So if at some point you say, you know, I've really got enough tasks running, I want to start ignoring these cobegins and coforalls and begins, the serial statement basically does that. And the other one is a sync statement that is used to dynamically join any generated tasks. So sort of over the entire dynamic scope of that sync statement, it'll wait for any tasks that were created to join. So it's sort of a big hammer for waiting for a bunch of tasks to complete. There are a couple of plan features that we didn't get into the first draft of the language, and we didn't think we would need or want. And in retrospect, we think we were naive. So some of the things we're adding in the next draft of the language are support for task private variables. So if you declare a variable A and then create a bunch of tasks, or sorry, if you create a task private variable A and create a bunch of tasks, they'll each end up with their own copy of that. That's similar to features in OpenMP. And the other is a notion of task teams, kind of like MPI communicators. So today, all tasks are kind of, in the eyes of the runtime in the language, more or less equivalent, homogeneous. They're all sort of in the same pool. But many algorithms may want to do sort of create blue tasks that have sort of one policy or one kind of interaction, and red tasks that maybe have some other policy interaction. So one of the things we're looking at doing, and I think Kathy alluded to work like this in UPC as well, is create a notion of a task team where you could say, OK, any tasks I create over here are going to be blue, and I can barrier between them or join them or do reductions across them or set a specific policy for them. And any other tasks are maybe red, and I can have different operations on them. So again, I think we were a little bit naive to believe that this homogeneous set of tasks was going to be sufficient. It is for very homogeneous codes and benchmarks, but once you get into real large coupled models where very different things are going on simultaneously, I think these task teams become pretty important. So next, let's talk about locality. I tend to view these as the lowest level features of the language because they're really the thing that are allowing you to talk about the target machine you're running on. So they're quite close to the target machine. And the key feature we have for locality is this type that we call the locale. And it's defined intentionally somewhat vaguely. So what you should think of the locale as being is when I'm running on this target architecture, the locale is a chunk of the architecture that is useful when I want to think about locality, when I want to think about what's here and close and cheap to access, and what's somewhere else and more expensive to access. So on almost every machine we target, typically the compute node is going to be the locale, because that's sort of the point where everything is relatively close together. And if you have to go to a different compute node, which is to say to a different locale, that's going to occur overhead because you're going over the network. So other than that, we don't say much about locales. We say that they can run tasks, which is to say they have some sort of processor, and they can store variables, which is to say they have some kind of memory. And other than that, sort of the exact mapping of a locale down to a machine is dependent on the compiler of the implementation. So when you are coding in Chapel, when you run your program, you can specify in the command line how many locales you want to run on. So here I've shown two different ways of doing that. Both of them I basically say I'd like to run on 8 locales, which again on a typical machine means I'd like to run on 8 compute nodes. Our locales hierarchy. So today locales are kind of flat. They talk about sort of what we call horizontal locality across nodes, but it doesn't allow you to talk about locality within the node, again, which is what we're seeing in next generation architectures. So a lot of our current work is designed around making these locales hierarchical. And again, I've got a batch of slides at the end, which we may or may not get to, but they're in your packet. And I'm happy to talk to people offline about it if they're interested. That's our main sort of current ongoing research thrust right now. All right, so today you say I want to run 8 locales. You get this set of 8 locales. Within the code itself, there's some built-in variables that you can refer to so that you can symbolically talk about the machine resources on which your program will ultimately be running. The first one is just a simple integer, num locales, which says, it'll be 8, for example, for these execution lines. And the second one, the more useful one, is you get an array of this built-in locale type. And so in this case, for example, we'd have an array that had 8 elements. Each element is one of these locale values. And again, those locale values are basically an abstract data type that represent the compute node, or the compute nodes on which we're running. And the other thing to know is that when you run your main routine, that the compiler and runtime are going to start running that on locale 0. So you're sort of guaranteed that your program always starts running on locale 0 out of this set. All right, so what do you do with these locales, these opaque types I've mentioned? Well, one of the things you can do is these provide our way of reasoning about and introspecting about the machine on which you're running. So you can say things like, how much memory does this locale have? Or how many CPUs does it have? Or what's its unique ID? Or what's its name? Things like that. And this is, you could obviously do this through system calls or whatever, but it's really kind of nice to be able to do this in a language way. In fact, we have some cute idioms where you sort of add up all the memory by all the locales in kind of a one-line nice reduction over this physical memory query here. So this allows you to reason about the machine. The other thing we do, and really the main thing we do, is that locales are how we talk about run this here, or run that there, or allocate this here. And that's done primarily through these on clauses. An on clause is another prefix that you can put on the front of a statement, and it basically says, run this statement wherever my on clause is telling you to do it. So these can either be done very explicitly, like here I'm saying on locales 1, right? Go over to locale 1 and run this next statement there. So my program starts running on locale 0, then it goes over and migrates to locale 1, and it comes back to locale 0 when I leave the scope of that on clause. Right? So this is a way to move the computation around the machine. And it's worth noting that the on clause itself is not parallel. Right? So this is still a sequential code. It's just a sequential code that's migrating around the machine as it's running. And again, philosophically, we think this is really important. Like locality and parallelism tend to be way tightly coupled in the models we use. Right? SPMD parallelism is talking about locality and parallelism all together. And that's one of the reasons it's hard to get nested parallelism and things like that. We think those two things should be separate. And so over here on the right, you can see an example of how you can merge these things together. I have a cobegin, which says create a task for each of the 2 statements within this compound statement. And do the first one wherever element a sub I, j lives, and do the second one wherever the left child of my node lives. And so the thing to note here is that these on clauses can also be data-driven. So you don't have to explicitly say, like, run on node 2, run on node 4, which is obviously a brittle way to code. More typically, what you'll do is you'll distribute your data, and then you'll say, go wherever element I sub j is of array A, and do this big computation that I know is going to take a lot of time there. Or go to wherever my left child is and continue this search that I'm doing there, as opposed to doing it here. And again, because that's orthogonal to parallelism, we're going to get 2 parallel tasks. They're going to go to wherever these on clauses say, and when they complete, then the cobegin will end. And that's kind of locales in a nutshell. Let me draw this back to the PGAS model that Kathy talked about to a great extent, and I talked about a little bit earlier. So as I mentioned, Chapel is PGAS, but unlike UPC and Cray Fortran, it's not SPMD. So when you're writing a Chapel code, you should never, like when you're writing UPC and Cray Fortran and MPI, you're often thinking about, okay, now what are the other copies of the program doing now? And in Chapel, you shouldn't be thinking that way. If you are, you're off to a wrong start. So instead, where the global namespace or the global address space comes from is just through normal lexical scoping. So in a traditional PGAS language, the reason I know that you have a variable x that I might want to refer to is because I have a variable x, and we're all running the same code more or less, right? It's sort of the nature of the SPMD program. And in Chapel, the reason I know you have a variable I might want to refer to is just through normal lexical scoping properties in language, which if lexical scoping doesn't mean something to you, it does. It's just maybe just not the term. So let me show you. We start running on locale 0, and we hit this declaration that says, declare a variable I that's an integer. And so I basically end up with an integer I on locale 0. Okay, then I have an on clause say, and it says, on locale 1, declare another variable j that's also an integer. Okay, well now I'm running on locale 1, so j is on locale 1. Now I can still refer to I even though I'm on locale 1 because it's in my lexical scope. If I just look up through the normal scopes, I see I. And therefore I can refer to it even though it's remote. So it's sort of, I would argue, a more natural way of doing a PGAS language than sort of the SPMD approach. And then things get even more interesting. I can do a Coforall. So this says, create a task for every locale in my locales array. This is a really common idiom. On that locale, do something, right? So I'm basically creating a task on every node. And so then I can do something like allocate a variable k that's also an integer. And what I'll end up with is every task will allocate its own copy of k on its own locale. Again, any one of those tasks can refer to j or I. If I created additional scopes and tasks within there, they could refer back to the k's of their parent. It's all just sort of the natural way you would do scoping in a language. So one thing that's kind of different about this than traditional PGAS languages is sort of the public versus private thing. You saw in UPC that sort of the shared keyword is the way of talking about, is this thing public or private? In Chapel, there's sort of a question of, okay, well, if it's just lexical scoping, what determines whether something's public or private? And the fact of the matter is, you normally don't think in those terms very much, because the thing that determines whether you're public or private is just what other tasks can see it, can see that variable, and then who actually bothers to refer to it non-locally. So for example, putting up the exact same code that I just showed you, I have tasks in that innermost loop that can refer to I and j. Therefore, by nature, I and j are public. K is completely local to those innermost tasks, and I don't have anything else inside of there that is remote or parallel. And so K is private. And so sort of inherently, this code suggests this kind of public-private breakdown. But again, if I were to put in some additional on clauses and tasks within that inner loop, suddenly those Ks are also public because things might refer to them. The fact of the matter is, we don't actually think in terms of public and private much. This is something the compiler takes care of. It sort of does the right thing. You just refer to the things you need to refer to and don't refer to the others. And that's the locality features in a nutshell. The two main things we have planned here, one is the one that the question was asked about earlier, this notion of hierarchical locales. So again, given that architectures are becoming much more interesting and complex and locality sensitive within a compute node, you really want some way within a locale to talk about, well, is it in this memory bank or that memory bank, or is it in the CPU or the GPU? And the hierarchical locales are designed to deal with this. And the other thing is just a notion of a locale private variable, similar to a task private variable, where if you refer to that variable, you're always referring to the copy that's local to your locale. And those are the locality features. So I've got a bunch of tasks in here, all of which could refer to I and j. We could get into trouble if those tasks started reading and writing I and j willy-nilly in an uncoordinated manner, right? We'd have potential race conditions, memory races, maybe memory consistency issues, things like that. And the short answer is yes, all of those things could happen. There's sort of a rich body of people studying, sort of creating race-free languages. We think having races in languages is actually crucial for a language to be truly general. So I think our attitude would be races are there by default. We might look at ways to sort of assert, like, this should be race-free, and please warn me if I have not succeeded in doing that or something like that. But today, Chapel is sort of very racy. So the way you would want to write a code sanely between multiple tasks is typically using synchronization variables as the main means in which they interact. And any other data you'd want to be read-only, essentially. But the language doesn't do much there. Basically, you can write racy code very, very easily. For example, if I had, instead of just reading I and j inside this inner loop, if I had this innermost thing write to I or j, it's basically a race to see which of those many tasks is going to win and have their value end up in I or j at the end of the loop. That's sort of the way the language is today. So now we get to move into the very high-level, very fun features. So data parallelism. The key feature in Chapel for data parallelism is this thing we call a domain. We call a domain. In my previous work on the language ZPL, we called it a region. And in both cases, this is basically a language concept that represents an index set. So you can think of it as sort of a set of indices that you're giving a name. You can assign to it, pass it around, all the normal stuff. And it sort of is, again, the fundamental concept in Chapel for data parallelism. So as an example here, I can declare a couple of constants, n and m, 4 and 8. And I can declare D to be a two-dimensional domain that's 1 to m, 1 to n. And so I end up with this little 4 by 8 index space, basically. And the way I've drawn it here, it looks a lot like an array. And that's not by accident. But unlike an array, there's not actually any data associated with those indices. So you can think of it as like the size and shape or silhouette or template of an array, basically, but without sort of order, m times n data stored in it yet. Just to provide another example, this is the declaration if you wanted to declare a second domain called inner. Here I've declared this type to be a subdomain of D. This means that it's basically the indices it describes are a subset of those that D describes. And I've declared it to just be 2 to m-1, 2 to n-1. So I get this sort of, as the name suggests, inner domain of D. So those are the most basic domain types in Chapel. And that gives you sort of these dense rectilinear domains. We also have strided domains, which are very useful in kind of multi-resolution algorithms like AMR or multi-grid algorithms, things like that. We have sparse domains, which allow you to represent arbitrary subsets of an index space. And that can be useful both for things like sparse matrices, also things like, this is supposed to sort of resemble the polar ice caps if you were to sort of discretize the Earth or something like that. So I could sort of say, these are all the indices that describe, surface area of the Earth that has polar ice on it. You can have associative domains, which are basically like sets of arbitrary values. Here I've got a set of strings, basically. And these, getting ahead of myself a little bit, are basically used to implement hash table-like data structures or dictionaries. And then we have what we call unstructured domains, which are designed to support pointer-based data structures. Okay, so again, in all of these cases, these are just sort of sets of indices, sort of abstractly, that you can name and talk about. And the things we do with these domains, one of them is, as you might guess, we use them to declare arrays. So there's a syntax that says, in fact, we've seen it. give me an array over this index set and of this element type, and then voila, you have data for every index in your index set. And then the operations you can do with these are pretty high level, and we've seen some of these in passing as well. So there are for all loops, which basically say, in this case, for all indices ij in my domain D, compute I plus j divided by 10, and assign that collection back to the array A. So what this will do is give every element in A a value that's sort of its row number dot its column number. You can also use these domains as a very rich way of talking about subdomains, and there's an algebra that they support that allow you to talk about creating new domains with respect to existing ones. So here, for example, I'm saying assign to the, and I guess I haven't kept the name quite consistent. This should probably just be inner based on my previous slide. Assign to the inner elements of A, which again is that domain of the inner indices that I defined, the inner elements of B shifted by this tuple 0, 1. Right? So I take the inner elements of B here, and I shift that domain's index set by an offset, and I'm basically going to assign element-wise those dark red elements to the orange elements in the previous. And as you can imagine, if you start using sparse domains on dense arrays, you can end up with some pretty interesting slicing patterns and accessing kind of arbitrary subsets of data in a very concise, and if you've named things well, readable way. We also support promotion of scalar operators and functions over arrays. So in this case, this is just the normal plus and times and assignment operator. This is the normal math exponentiation operator. All of these things are only defined on scalar values, but you can give them array arguments, and basically what will happen is we'll compute those values on every array argument. So this is sort of a very concise way of writing the stream triad benchmark we saw at the beginning of the talk. And this just says take every element of B to the corresponding element of C power and assign the result to A. I should mention that even though all of these things are built in here, you can write your own user routines as well and promote those as well. And that gives you a map-like capability. And then there are a bunch of other data parallel and domain and array operators that I'm not going to go through. Kind of the things you'd expect: indexing, reallocation, various set operations, reindexing, maybe I said that twice, so on and so forth. Kind of, if you would want to do it in a rich array language, we probably can. So let me just make a couple of notes. One of these is these for all loops. So before now, we've seen for loops and Coforall loops. Now I've thrown for alls into the mix. Let me kind of distinguish them. So for loops are completely sequential. One task runs the whole thing. Coforall loops create a task per iteration. So you're basically going to get as many tasks as you have trips in your loop. And for all loops are kind of somewhere between those two. And the language doesn't specify, but you as a programmer can go in and specify how many tasks to use. But typically by default, if you don't go to any effort, the number of tasks is typically going to be proportional to the amount of hardware parallelism that you have. So for example, if you were running this code on a my 4-core Mac, for example, then I would get 4 tasks that are dividing up that index space. If I were running it across the whole cluster, it would be however many cores were in the whole cluster, or in the locales that I owned of that cluster. The other thing about for all loops that's a little bit interesting is you can invoke these with Zippered Iteration, and you'll still get a data parallel implementation of those loops where sort of the matching things will line up. So it's not like I'll have an arbitrary element from A and an arbitrary index from 1 through n and match those up. It'll sort of, like the name suggests, they'll zip together kind of the way you would expect. And then one other thing I wanted to say about the data parallelism is a little bit more about these promotion semantics. So whenever we have one of these promoted operators, like again, equals here is basically a scalar operator, but we're assigning it to 2 arrays, so that ends up being a promotion of that scalar equals operator across all of the array elements. Anytime you see these promotions, they're basically equivalent to a zippered for all loop. So for example, this very concise statement, A equals B, is equivalent to for all little a, little b in the zipper iteration of big A, big B, assign little a, little b. Okay, so there's sort of always a one-to-one correspondence between these promotions and for all loops. Let's look at a slightly more interesting example. Here's the stream example again. Array A gets array B plus alpha times array C. That's going to be rewritten to do a zippered for all loop for all little a, b, c, and big A, b, c do little a equals little b plus alpha times C. And this can be a little bit confusing. I think it's good, but sometimes it catches people off guard. If you're used to working in array languages, people are often expect these operators to be evaluated the same way they would on scalars, which is to say, first I'm going to multiply C times alpha and store that in a temporary array. And I'm going to take that temporary array and add that to B and assign the result of that to my result A. But Chapel doesn't do that. We really take these for all semantics here. And the reasons for that are that we've defined a semantics in such a way that temporary arrays are not required by the language. The compiler should never insert a temporary array without you explicitly requesting it to. And the reason for this is a lot of people's programs, they basically say, if you say, how much memory do you want? They say, well, how much do you have? So they're going to take the amount of memory on the machine and budget like, OK, then I can have this many arrays of this size. And if the compiler introduces one temporary array, it can blow your whole memory budget, right? and kill your performance as well. This tends to have better, the zippered for all up at the top tends to have better cache behavior than if I sort of am ripping through my arrays pairwise and completely blowing my cache out each time. Okay, so these are the reasons this is a good thing. It can be a little bit surprising though. Here what I've done is I've written a kind of 3-point stencil idiom using whole array operators. So I've said for all elements in D, or maybe I could have used inner there if I'd had more space, assign it to D shifted by 1 down and D shifted by 1 up. So I'm kind of doing almost an averaging thing, except I'm not actually averaging. And if you took an array semantics, this would be like, oh, I'm gonna add those two shifted things together and then assign them to the original. But because we take the zippered for all semantics, and because I'm using the same array on both the left-hand side and the right-hand side, this actually is a data race, because at the same time, some task may be overwriting some of the values that haven't yet been read by the other. So this is just something to be aware of. In our experience, this doesn't actually come up much in practice. But again, if you're thinking in terms of an array language semantics, this is a way in which these zippered semantics differ. If I have a compiler optimization that relies on, for example, inserting a temporary array or something like that, have I disabled the ability to write that operation? I guess the way I would say it is that the language is designed so that the language never requires the compiler to insert temps. A compiler could insert a temp if it thought it was a wise thing to do. And presumably the compiler should be written in such a way that if at execution time there isn't actually enough memory for that temp, it has some sort of fallback that it could use, because it ought to be a correct program without that temp. I think what tends to happen more in practice, though, is that rather than allocating a temp of the entire monolithic data structure size, most compiler optimizations, at least that I work with, are typically some smaller slice that's asymptotically much smaller than the total problem size. And something like that would be completely fair game, and something that wouldn't affect your memory budget overall, typically. So I think that's the more common case, and that's certainly as well within the legality of the language. Yeah. If you guys are good performance-oriented programmers, at some point you should ask yourself, well, these arrays look very nice and very elegant and beautiful, and you've got nice operations on them, but I'm a performance-minded programmer, and so I want to worry about things like, how are these laid out in memory? Like, for example, if I'm interoperating with C or Fortran, I might want to know, is it row major or column major order? Or have you guys done something even fancier, like some sort of space-filling curve to lay out the arrays? Or maybe you've got some sort of hierarchically tiled data structure, something like that. Similarly, if you use our sparse arrays, and if you're a sparse matrix kind of person, you might say, do you use a coordinate data structure, some sort of compressed sparse row, some sort of blocked data structure, something like that. And then another thing you might ask is, if I'm running on multiple locales, and I declare an array, how are these arrays mapped down to the locales? Are they going to be completely local to a single locale? Are they going to be distributed across locales? If they're distributed, how are they going to be distributed? Block or cyclic or block cyclic or something else? Even if they're blocked, there's sort of a lot of different ways you can block things up. Again, very important questions from a performance standpoint. And the answer here is kind of yes. Like, you can do any of these things is sort of the goal. So unlike C or Fortran, which kind of dictate how arrays are laid out in memory, Chapel's been designed in a way that sort of is very, very clearly does not say much about how things are laid out in memory. And in fact, the concept that we started the talk with, these domain maps, are basically designed to give you, the user, full control over these decisions. How should things be laid out in memory? How should they be distributed across the locales? And that takes us to our last language feature area, which is these domain maps. Domain maps basically are these recipes that allow me to write this really high-level global view code like we saw at the beginning of the talk. And what the domain map is responsible for is saying, how am I going to decompose that data and work down to my locales and the processor cores that they own? So here's one possible mapping, and there may be other possible mappings as well. And at this point, we can return to stream Triad, and you've now seen enough features that it'll make good sense to you. I started out by declaring a domain called problem space. This is just the indices 1 through m that define my problem space. And then I declared 3 arrays, A, B, and C, which are arrays over the problem space domain of reals. So I now have 3 data vectors over my problem space. And then I can write my computation. Here I've done it using promotion, so I just say A equals B plus alpha times C, and that gives me the computation I wanted. And so now we ask the question, well, how is this actually going to be implemented on the machine? And the answer here relates to the fact that when I declared this domain, I didn't specify any domain map for it, right? I just declared the domain. And so what's going to happen in the implementation is that there's always a default domain map that if you don't specify one, the implementation will fall back on instead. And in our current implementation, the default domain map basically always targets only a single locale. So you'll never end up with a shared memory data structure, or sorry, you'll never end up with a distributed memory data structure unless you explicitly request it. And then any computation over, say, loops over that domain or arrays declared over that domain are all also going to be local to that locale. So what this means is the code as I've written it here is basically a perfect shared memory parallel code. When I do my promoted operation there that's equivalent to a zippered for all, I'm basically going to use all the processor cores within my current locale, But if I'm running on 10 locales, the other 9 locales are going to be idle, basically. So if I want to turn this into a distributed memory code, what I'm going to do is throw a dmapped clause in here. And dmapped basically takes a constructor for a domain map, and it sort of instantiates a copy of that domain map. And so here what I've done is used one of our most common domain maps, common, I think, in the community, which is called block. And the block domain map is going to basically say how to take this index set and divide it across the locales. And these domain maps can have sort of arbitrary arguments. And the block has an argument that basically says, well, if I think of the infinite space of indices, which ones of those should I consider when I'm blocking things up across my locales? And the argument here basically says, well, please use the indices 1 through m. So what I'm going to do is take that subset of the infinite index space, and if I'm running on 4 locales, I'll block it up across those 4 locales. And because I've applied that domain map to this domain, it's going to block up the indices of that domain. And because these arrays were declared over that domain, it's going to block up the indices of those arrays. Okay, so by changing that one line, I've basically changed this from a shared memory multi-core code to a distributed memory multi-core code. And within each locale, it'll still use all of the processor cores that are there. And then we can say, well, maybe block isn't right for this problem for whatever reason. It actually is. So maybe we want to demap it using cyclic instead. And cyclic has a different argument list. With cyclic, it's basically just a round-robin dealing out of indices. So you basically say, well, which index should we give to locale 0 as we start dealing these out? And so here I've said, we'll give 1 to locale 0. So we'll just deal them around cyclically. And I don't have a really good way to draw this, so I've used different colored lines to sort of represent the cyclic distribution of these indices. And that's going to be inherited by the domain, and again by the arrays. And again, it's going to result in distributed memory multi-core execution of the code. It's just that you own a different subset of the indices than you did in the previous slide. And as I alluded to, these are both fairly simple static cases and easy to draw. You could also have a domain map, for example, that dynamically load balance the data or things like that. All you have to do is name it, and you have a completely different implementation. All right, so we've already seen these block and cyclic distributions. This slide just shows that they can be used in a multi-dimensional manner as well. And you can basically take the set of locales that you're mapping and pass those in as an argument optionally if you want to. Or by default, the implementation will just make them into kind of a squarish kind of rectangle. So here if I say block my 1 to 4, 1 to 8 domain in a blocked manner, basically I'm going to get this 2-dimensional blocking of it. And if I do cyclic, I get this 2-dimensional round-robin dealing out of indices. All of the different domain types we saw here support domain maps. So for a sparse case, you may want to use something like a recursive bisection or something that actually goes and inspects the data to distribute it. For associative domains, we tend to use hash functions. For unstructured domains, the concept would be to use a graph partitioning algorithm or something like that. But the point is that all of these can be distributed across nodes. All right, so at this point, let me talk a little bit about our philosophy of these domain maps. Can I have multiple mappings coexist simultaneously for data? So every domain has a single domain map associated with it, and that domain map is part of its static type. So a domain cannot change domain maps over its lifetime. Therefore, typically, if you want different distributions over the lifetime of a program, you would typically, like for example, if I want to change something from block to cyclic in an FFT algorithm or something like that, typically what I would do is there'd be some phase in the program where I would sort of slosh from my block domains and arrays over to my cyclic domains and arrays and deallocate the other one. The other thing you could do if you were sort of a heroic domain map author is you could write a domain map author that was sort of a multi-mode domain map. And if it had all the logic within it as how I could be block or cyclic, you could have methods on it, for example, that said, hey, change yourself over now. And it could sort of reshuffle things under the covers. So that would be sort of a software engineering way to do it. But from the language perspective, each domain can only have a single domain map for its static lifetime. Let's say we've got a distribution of our domains and arrays, like this here. When I compute on these arrays, I would like the tasks to be executing on the locales close to the data that they're accessing. That's more or less what you're asking, right? So the question is sort of, well, does that happen, or how does that happen? So if I use for all loops, or because promotions are equivalent to for all loops, promoted operators like these, for all loops on domain maps are typically written in such a way that they create the parallelism in a way that sort of respects locality. So in fact, if you were to open up the block domain map and say, how is the for all implemented there, what you would see is that it does a Coforall across all the target locales, and then an on clause to move those tasks to the respective target locales. And then it would do a Coforall for all of the cores within that locale, and then it would make sure that those only operated on the indices that they owned. You can still cause communication, though. So let's say that A and B were implemented with a block distribution, but C was with a cyclic distribution. In that case, obviously, one of those two distributions is not going to be respected, and so you'd have communication to bring the other elements over. So you could still write a statement like the one here at the end. It's just that you wouldn't have that same locality property that you had before. So I was going to talk about our philosophy here. So when you download Chapel, what you get is a standard library of domain maps, common things that you would expect like block distribution, cyclic distribution, compressed sparse row, sparse layout, things like that. And today that's actually a pretty small library. The intention is that it will grow over time. So the idea here is if you have a common data structure, common distribution, you should just be able to use that out of the box and be happy. The second part of this philosophy is that if you're an advanced user, and let's say you have a very clever way of laying out or distributing your data that we didn't anticipate in our standard library, you should be able to go write your own domain map in Chapel. So these domain maps, as I mentioned at the very beginning of the talk in the multi-resolution philosophy, are implemented within the Chapel language itself, and they're implemented in terms of the lower level features. So for example, we were talking about the for all loop for the block distribution. It uses coforalls from the task parallelism, on clauses from the locality control, objects from the base language, and that's how it's all implemented. And so the point here is that there should never be a point when you say, oh man, if only I had this fancy sparse distribution, my algorithm would be great, but because you didn't think of it, I'm screwed. You can go in and write that yourself, is sort of the idea. I'm not saying it's easy, but having written it, then you can contribute back to the community and other people can benefit from your work. And then the third part is that all of the standard domain maps from category 1, the ones in the standard library, we are writing using the same mechanism that you as an end user would. And this is basically an attempt to keep ourselves honest or eat our own dog food, if you like that phrase. Basically, we didn't want to have this situation where things like block and cyclic and compressed sparse row were all built into the compiler and runtime and performed great. And as soon as you went and wrote your first domain map, you fell off this performance cliff from which you could never recover. So to kind of ensure that one can write domain maps in this framework within the language and get good performance, we're sort of holding ourselves to that same approach. This next slide, I'm not actually going to go through. It's pretty detailed. But at a high level, what it's showing you is if you want to write a domain map, what you essentially do is you write 3 classes. We call them descriptors. One describing the domain map itself, one describing the domain or any domains declared over that domain map, and the other describing any arrays declared over those domains. And what you essentially need to do is provide this required interface for each of those classes. And having done that, that's the interface the compiler is going to target as it's writing these high-level for all loops and promoted operations and global view operations down to kind of the per locale data structures and tasks and things that are needed to write it. Okay, so the way you implement those is kind of completely up to you, and that's why you end up with such, in terms of the data structures used to represent these things, it's up to you as long as you provide the required interface. And that's what gives you so much richness in terms of what you can express in this framework. This next slide is a little bit of an old result, but this is designed to show that you can use these domain maps without completely destroying your performance. This is the stream Triad benchmark that we start out the talk with. And there are 3 versions running here. 2 of them are embarrassingly parallel, where you basically create the parallelism first, and then you start the timing and you compute only on local data structures. And those are the EP versions. That's the version that MPI provides as a reference, and we wrote a version like that in Chapel as well. And then the other line, the dark blue, is the Chapel global line. So that's using a block distributed array and a for all loop. And so essentially it's a little bit slower because of the fact that that for all loop, the sort of creation of the parallelism across the whole machine, is now within the timed portion of the code rather than being amortized out as it would be in MPI or the EP version of Chapel. So what you can see is that these for all loops can scale reasonably well, although you're obviously going to take some overhead for starting up the parallelism. But generally it's pretty competitive with standard MPI and an EP version of Chapel. Now there's a big caveat here, which is that Stream, again, is an embarrassingly parallel benchmark. There's no communication. If you have something that does require communication in Chapel today, that's one of the areas where the performance is not quite yet as good as it needs to be. We're not very good at optimizing communication yet. And so if I were to take, for example, a 3-point stencil and compare MPI to Chapel, you would see the Chapel doing much worse because the communication we tend to do is much more fine-grained, demand-driven, less well amortized than it is in most MPI implementations. So that's future work. And I should say, something we've had a lot of success with in our previous work on the ZPL language. So it's a matter of kind of bringing that work forward to the Chapel language, which we just haven't gotten to yet. If you're interested in learning more about these domain maps, getting into them in more detail, I've noted a couple of papers here that describe them. And then if you download the release, I've pointed to places in the code that they're both documented and where you can go in and actually look at the code that we use to implement block distributions and sparse arrays and things like that. This next slide basically talks about, we have some ideas about more interesting advanced ways to use these domain maps other than just sort of simple static mappings like block and cyclic and sparse and things like that. So this just mentions some of those. And also I mentioned the additional communication optimizations we need to do here. So now I want to get back to the question that was asked about sort of who owns work in a parallel loop. So a second performance-minded question that you should ask yourself when you see a for all loop, we talked about a little bit earlier, is when I see a for all loop like this, how many tasks are executed are used to execute that loop, and where do they execute? And how is the iteration space, the index space, divided between those tasks? And a second one you might ask is, with these parallel zippered loops, how are those implemented? So if I'm zippering over A, B, and C, and they all have different distributions or different domain maps, like how in the world, what determines, again, where the tasks run and how things are executed, things like that? And the answer here is similar to with domain maps. So the idea is that you should be able to come up with sort of any decomposition of for all loops across tasks and the work across those tasks and do that yourself within the language. And the features here that we use to do that are called leader-follower iterators. So the idea here is that every time we have a for all loop, we say that one of the things you're iterating over is the leader, and the other things are the followers. And the leader is the thing which basically gets to decide all of the policy for the loop. How many tasks should we run? Where should those run? How are they going to divide up the iteration space amongst themselves? And so conceptually, whenever you have a zippered iteration, the first thing being zippered in is the leader. And if you have a promoted operation, you sort of rewrite it into the equivalent for all loop, and then you can figure out which one the leader is. So here, A is the leader, and then all of the things that you're iterating over are also followers. So A, B, and C are all followers. So the leader is going to say, for example, let's use 8 tasks, and let's compute the workload statically blocked. And so that's what I want all of you followers to do. And the follower is just responsible for basically doing that work, essentially. Oh, so here's actually rewriting that loop more explicitly. What we're going to do is basically invoke A's leader iterator, and it's going to yield chunks of work. And then inside of that, we're going to use a sequential zippered iteration to call the followers of A, B, and C, passing them that work and saying, please iterate over this subset of the iteration space. And then they're going to yield out their values. And that's how we sort of rewrite this for all down into lower level concepts. So the leader iterator is typically going to use task parallelism and maybe the locality features. So I was sort of talking to this code in the air before, but here you can see it in front of you. This is the leader iterator for our block distribution. And you can see this idiom that I said is very common in Chapel. We do a coforall across all the locales, an on clause to move each task to its locale, and then a coforall for all of the cores within that locale. And then we basically have this helper function that computes, given my locale ID and my task ID, what subset of the iteration space do I use if I just block things up? And it's going to yield that, and the followers take that work in as their input argument and basically just serially iterate over that and yield the elements corresponding to it. So alpha is just a scalar, and the language semantics would say that alpha sort of only lives on the single locale on which it was allocated. But typically alpha would be a constant or at least invariant for the lifetime of this loop. So that, as an optimization, the compiler is typically going to replicate that. In fact, when it fires off this coforall that creates a task per locale with that on clause, when the compiler sees constant values going across an on clause, it actually passes the value along, typically, with the task that implements that coforall. So the alpha will sort of be carried along as one of the implicit arguments to the tasks implementing that coforall. OK, so that's how you write leaders and followers. And again, note that we're basically implementing high-level data parallel features in the language using the lower-level features, the task parallelism, the coforalls, the locality control, the on clauses, and the base language, these iterators and yields and things like that. All of the data parallelism is implemented using these kinds of concepts in the language. So when we put it all together, that high-level for all loop there is basically going to be rewritten into an inline invocation of the leader iterator, the zippered invocation of the follower iterators, and again, we've sort of gotten rid of anything that's data parallel in that statement, and now we're down in the lower-level task and locality features of the language. Again, there's sort of a question, well, what if I don't like the approach that's implemented by the leader in my loop? So one possibility is you can basically reorganize the things you're iterating over and make something else the leader. So for example, if A uses a static blocking and you don't think that's a good idea, and if B by default uses a dynamic blocking or something like that, you can make B the leader. Another thing you can do is you can change the domain map of one of your arrays. So you could say, oh, well, let's make the leader array block cyclic instead of block or something like that. Each domain map comes with a default leader follower iterator that's used when you iterate over the array. And so now you've basically ended up with a different leader follower here. And the third thing you can do is you can write your own leader follower iterators, either within the domain map framework or just standalone iterators. So for example, we had a colleague from the University of Malaga in Spain who basically wanted to reproduce all of OpenMP's dynamic kind of work balancing kinds of schedules in Chapel. And so what she did was she wrote them as leader follower iterators, standalone language. So there's one called dynamic, for example, that would take, it actually takes a range, although my slide here takes an array. We've been meaning to extend it to arrays, haven't gotten there yet. So it takes a range and then a chunk size. And basically what it'll do is the leader will sort of yield out chunks of work at a time of that chunk size until all the iterations are done. You probably heard about this in the OpenMP lecture this morning. I didn't make it for that. So it's sort of semantically the exact same thing. And what she found was that we could get performance that was essentially identical to or very competitive with OpenMP. And the really cool thing here is that we've done that without sort of baking it into language, right? So if you had a new loop distribution policy and you wanted to get it into OpenMP, you'd have to start meeting with Brannis and convince him to adopt it into the language. Then you'd have to start meeting with the OpenMP implementers and get them to implement it. And then you'd have your new sort of really snazzy dynamic iterator or whatever. In Chapel, because you can write your own leader-follower iterators, you can create very clean for-all loops that are implemented using your schedule without changes to the compiler or the runtime and such. You do it all within Chapel. And an example of this was done by that same colleague. She basically had an idea of an adaptive work stealing load balancing algorithm that she wanted to use that's not supported by OpenMP. So she implemented that in Chapel and showed with some of these artificial workloads that you could get better performance than you could with the OpenMP versions. Again, without changes to the Chapel compiler, runtime, or language. So the takeaway here is that these for-all loops in Chapel can be competitive with OpenMP, and in fact, from the stream Triad example I showed before, competitive with MPI as well, as long as there's not too much communication today. But rather than baking them into the language compiler and runtime, you're specifying them in the user-level Chapel code. So some pointers here. If you want to learn more about this technology, we had a paper in PGAS a couple years ago which describes it. And again, I've got pointers in the release here of both a primer example that sort of walks you through this in a bit more detail, and then you can look at the library of iterators that colleague from Malaga wrote that summer. So to pop up and summarize this whole section on domain maps we've been talking about, philosophically, Chapel has worked very hard to avoid locking crucial implementation decisions into the language. So things like how are arrays implemented, and how are they distributed, and how are they laid out in memory, how are parallel loops scheduled. The language says really nothing about all those things other than the implementation will say something in the default case. And instead it says, you can have sort of anything you can implement with lower level language, and you can specify that yourself as a user in the language. And this has really been the big research thrust of this program for the past 10 years or so. So you can go and play with all of these concepts now. And again, this is the key thing that we think separates appropriately the sort of domain scientist from the parallel expert, from the compiler and the runtime, allowing each to focus on what they do the best without kind of getting it all glommed together in the code. And that completes your tour of the Chapel language. So are there any questions there? My last few slides here are basically kind of, you can tune back in if you've gotten lost. We're going to talk about at the meta level, where's the project today, where's it going, things like that. And then I am definitely not going to get to that bonus section, hierarchical locales, that I talked about earlier. But again, the slides are here, and I'll maybe just give you one or two teaser ones if time permits. So what's the status of Chapel? So we do releases about twice a year, and the most recent one was in April. It's version 1.7. And overall, everything you've heard about today pretty much works at a functional level. There are a few slight caveats, like we don't actually have any distributed memory unstructured arrays and domains yet. There's nothing in the compiler that would prevent that. Nobody's just written that domain map yet. But pretty much everything else you've heard about today, particularly in the core language, works. You can try it, you can kick it out. Oh, and again, I forgot, as I thought I would. I'm happy to demo some of that interactively if you'd like, time permitting. Some of these features probably need to be improved. There's some things we didn't quite get right the first time. Some of our object-oriented features are kind of iffy. I mentioned task teams as something else we forgot about. So things we want to go back and improve, but by and large, you can sort of kick the tires and try things out. As I alluded to once or twice during the talk, there's still lots of performance optimizations that remain. Sometimes we do quite well, and I've shown you some of the good cases here, and we're very competitive with sort of conventional technologies. In other cases, we fall off a cliff. And it depends a lot on the style of application you're using, as well as, to an extent, how much you sort of tread the line that we've studied a lot so far. So what I usually tell people if they say, should I be using Chapel today, is if you have some critical application that your job or your degree depends on, probably not. But what I'd really like you to do, if you have a chance, is to kick the tires, try out some idioms that are sort of come up a lot in your code, and sort of see if you like what you see, or in particular, help us course correct if you think we're doing something wrong. But if you have something that you're working on that's not performance critical, or you're not going to lose your job over, you have some time to play around with things, this is a great time to kind of try things out. I mean, you can do almost anything the language wants you to do today. It's pretty cool, because it's taken us a while to get to this point. And again, we're interested in your feedback. The other thing is, I know some of you are in the education business here. If any of you teach classes in Parallelism, I think Chapel is really great for education. In particular, so I used to say, if I taught a parallel class, these are the things I want to cover. And then UW actually made me put my money where my mouth is. So last winter, I taught a class, and I wanted to cover all these topics and then some. And when I think about it, we just don't have many good technologies for teaching all of these things, and in some cases, not for teaching any of them at all. Right? So you want to teach about data parallelism, task parallelism, concurrency, synchronization, races, performance tuning, distributed memory, shared memory. What are you going to use? Like, MPI is not that educational. OpenMP, no offense, is not that good at large-scale things. So you can pick different technologies for different aspects of this, but if you wanted one thing to use for your whole course, you're kind of stuck. And I think Chapel could really play a big role here. So in my class, I used Chapel, and I also used conventional technologies. So I would teach them MPI and then Chapel, OpenMP, and then here's how you do that in Chapel. And for a lot of the things, we made them do one assignment in each technology, but then we would give them their choice for a third. Like, you can do this one in either OpenMP or Chapel. You can do it in either MPI or Chapel. At the beginning of the quarter, the students were highly skeptical, as you might imagine, like, oh, this guy's pushing his personal pet technology on us, like, we'll humor him or whatever. And there's a lot of skepticism about it. But by the end, when we gave them a choice, like, it would split 90-10. 90% of the students would do it in Chapel, and 10% would do it in, the conventional technology. That's how much they enjoyed it, found it useful, and allowed them to focus on sort of the core concepts and not all the details of parallel programming. So that's my advertisement for using it in classes. Here's a family portrait of the Chapel team as of last summer. Here's the broader Chapel community, and this is a pretty big laundry list. But the point is, there's a core team at Cray. We're currently 7 or 8 people, and we're trying to grow it up to about 12. But then both domestically and internationally, there's a large community, again, of academics, national lab people, a few people in industry, working in a lot of interesting areas that we don't have time within the core team to do. So again, something to refer to offline. If there's a collaboration area that you think we don't have covered and you think would be interesting, we're always open to new collaborations, assuming they make good mutual sense. We've kind of just wrapped up HPCS in the past 9 months or so. And so we're now looking forward to kind of the next 5-year period. And our main goals here are to harden our prototype implementation to be production grade, basically make it so that in 5 years I can say, yes, you should be using Chapel for your crucial application or dissertation or whatever. And the main things here are improving the performance and backfilling any features that are lacking or missing. We also need to target these more complex and modern compute node types, things like GPUs and mics. These weren't part of the HPCS program, so we're kind of behind where we'd like to be there, but we're catching up as quickly as we can. We're also doing a certain amount of work in the next 5 years to continue to grow the user and developer communities, looking particularly outside of HPC at mainstream programmers and big data programmers. And we're also looking at how do we transition Chapel from a Cray-controlled project to more of a community-controlled project. So we think that's necessary for its long-term survival. And then, as I mentioned, we're working on growing the team at Cray. So we currently have 4 positions open, a manager, a couple software engineers, and a build test release person. If you guys know of graduating students, or if you yourself happen to be graduating and you're interested in this, please send your friends or yourself our way. So to summarize the whole talk, higher level programming models, I think, can really help insulate algorithms from parallel implementation details. Let you focus on parallelism and locality and not focus in every line of your algorithm about how to map it down to the machine. But you can still do that, it's just in a separate part of the code. We think through this, Chapel can greatly improve productivity, both for current and emerging HPC architectures, and also in mainstream parallel computing. So if you want more information on Chapel after today, there are a couple of web pages here. The first one has kind of high-level overviews, papers, presentations, language spec, things like that. And the next one's where the code is actually hosted, where you can download the release. There are a bunch of public mailing lists there as well, which are shown in green down here. So I've shown the main mailing aliases down here. And if you want to go read 1 or 2 things about Chapel, these are sort of my suggestions. These are 2 overview papers that were written in the last year or so. This first one is higher level and shorter. The second one is more detailed and actually goes through a lot of these themes and concepts I talked about in today's talk. You could view this almost as the paper version of this talk with more detail. And then if you really like my philosophies, if you're not sick of them after 2 hours, last year one of the guys at Argonne twisted my arm into writing this series of blog articles that ended up being called 10 Myths About Scalable Programming Languages. So often when you're me and you're going around talking about parallel languages, everyone's going to tell you why your language is going to fail. And that's reasonable because, of course, getting languages adopted is an uphill battle. But a lot of the technical reasons people give, I think, don't hold up. So I think a lot of getting a language like this to succeed is deciding that we as a community want a language like this to succeed. And so this blog series is basically me trying to bat down any technical objection to whether or not a language can succeed. And then that's basically the end of my talk. Again, I had some extra slides in case we got to them, although I rarely do, that talk about, OK, back to the beginning of the talk, these exascale architectures, how are we going to deal with those? And the short answer is basically we're going to take that locale concept we had, make it hierarchical so you can talk about realms of locality within locales, and make the specification of that nesting another thing that a user can specify. So in the same way that you can specify a domain map today or a parallel iteration schedule, you can say, this is the nested block diagram I would like to use to represent an Intel mic or an NVIDIA echelon or something like that. And what you would say is, here's how you run a task on that sublocale, here's how you allocate memory on that sublocale, the compiler targets that interface, and suddenly we're running on those. So that's the work we've been doing currently, is basically taking a bunch of stuff that's baked into the compiler and runtime about locales and moving that out into Chapel code, much as we did the arrays and iterators.